One of our major concerns these days as far as the environment goes is air pollution. We have some cities that are really smogged in, and you see in the summertime you have ozone alerts and things like that. And in fact, the incidence of things like lung cancer or even things like asthma, which are directly affected by air pollutants, is a major concern today. So it's very important that we understand how air pollution works, especially with regard to weather. And of course, weather affects us all and is probably the biggest topic of conversation in the world. So we're going to take those two things today, we're going to hook them together. We're going to show you how weather works, basically, and then how different weather conditions can affect what type of pollutants we have during the day. So this will be a real practical lab to help you to decide, to understand what the weather's like and when you have to be careful of air pollution. The atmosphere is a big envelope of gas that is adhered down to the Earth's surface only because of the mass of the Earth. So the mass holds the atmosphere down, and it's densest closest to the planet and gets thinner and thinner as you go up into the higher and higher elevations. Now, because things are hotter at the equator and colder at the poles, you tend to get a circulation going. Okay, so cold air tends to sink at the poles and it rises at the equator because it's hotter. And so therefore we get rising and falling air within the atmosphere. Now, that would be the simple system if we just had things falling at the poles where it's cold and rising it where it's hot. That would be the simple. However, we have another factor that goes into this, and that is that the Earth spins, and we get what is called the Coriolis effect. Now, the Coriolis effect goes this way. If you're standing at the pole, imagine what happens to you during a day, okay? All that happens is this. You spin around. If you're standing at the equator, you go 24,000 miles around. So you move 24,000 miles in a day. That's 1,000 miles an hour, as opposed to just spinning around in circles at the pole. And so what happens then, because of this differential movement, as something travels from pole to equator, it will necessarily pick up speed and also be deflected. So as the Earth spins, and if you were to like to say shoot a missile from the pole towards the equator, it would necessarily, the Earth would spin out from underneath it. And that is the Coriolis effect. It means that things will divert as they move from north to the equator. And so therefore, that is part of what affects our weather patterns. This causes things to spin, okay? And so therefore, most of our storms spin. So for example, if you see a big low pressure system in the northern hemisphere, that's where we are, it will go counterclockwise. A high pressure system will go clockwise, okay? So you get counterclockwise for low pressure, clockwise for high pressure. And that's only because whether the air is rising or falling. Okay, falling air is high pressure, that's going to spin clockwise. Rising air is low pressure, it's moving away from you, it spins counterclockwise. If you go to the southern hemisphere, it's dead opposite. As the air rises, it will spin clockwise instead of counterclockwise. That's because they're converging in opposite directions as you go from south to north or north to south. And that's how we get. So we get these spinning zones. Now, you've seen that if you flush the toilet, for example, you notice how it spins in the toilet bowl. That's because of the Coriolis effect. And so if you ever go on a cruise ship and you're going across the equator, the best thing to do is to go flush the toilet because it'll go straight down. It doesn't spin at all. Okay? So that's one of the things you can check to see how Coriolis effect works. Now, once we have that in place, now we have kind of different zones. It breaks it up into zones where you get rising air and falling air. So at the equator, air rises. About 30 degrees north, air falls. And that's where all the deserts of the planet are. 60 degrees, it gets wet again. We get rainforests again. We get some northern rainforests, like in the state of Washington and places like that. Go up to 90 degrees at the pole, and you're dealing with desert again. Even though there's a lot of water frozen, very little falls per year. And so therefore it breaks it up into bands that become climate bands. And that's how the basic Earth sets up. Now, in terms of our local weather, that affects us too, but the big thing that affects us is air masses. If air sits for a long time over a certain zone, it will take on the characteristics of where it's formed. So for example, if you form a bunch of air over Canada, Okay, it tends to be cold and dry. After all, there's no water up there to speak of. As opposed to Gulf Coast air, if it forms over the Gulf of Mexico, it will tend to be moist and warm. Okay, and what happens is these masses of air, once they're made, can move around and interact with each other. And where they interact is what is called a front. Okay, so where the two masses of air come together, bang, you get a front. You're standing there, it's a warm, moist, you get a lot of humidity, it's warm and moist. Then all of a sudden a front comes through and it's replaced with cold or dry air. That is a cold front. If, on the other hand, you have warm, moist air replacing cold, dry air, that is a warm front. Now the big thing is this, is you get different precipitation and total weather patterns based on the different type of front that comes through. So for example, if you have a cold front, you tend to get a very steep angle between the cold air and the warm air. And so therefore, because it's steep, all the action takes place at once. So when you see thunderstorms, for example, and things like that, all of a sudden you'll come in, you'll get these real big cumulus clouds, big heavy things, heavy winds, heavy rain, and it will be over in no time. Okay, and all of a sudden at the end of it, it'll get much colder. And so that's a very short, intense weather pattern to get a cold front. As opposed to a warm front, where the warm air rises up over the cold air in a wedge-shaped pattern, and on that wedge, what you will start up by getting, in fact, you can see a warm front coming. Because if you look up in the air, you'll see a ring around the sun. Or maybe you see what are called sundogs, little pieces of rainbows on either side of the sun. That means you're getting a little thin veneer of warm air coming up over the cold air. And then as it gets slowly, it'll get cloudier and low. The clouds will get lower and lower, and all of a sudden you'll start to get misting, and then finally you'll start to get the rain. And after the rain, it'll rain for a long period of time, and then slowly it'll clear out. And so therefore what you wind up with, that is a warm front. It's a much different weather pattern. None of the intensity, no thunderstorms, not much in the way of wind. That's the type of weather pattern we're looking for a warm front. So you can see the differences and changes in precipitation, in wind, in temperature, in humidity. All of those things change across each one of these fronts, and they all go together in a package. Here at Rutgers, we had a weather station set up on the roof for a long time. And what we did was collect a lot of weather data. Now nearby, the DEP had a station where they collected information on pollutants. So what we did was we took a couple periods of time, and that's what you're going to look at here, 2 periods of time. We've graphed everything, all of the weather features and all of the pollutant features. Now what you're going to do with these is you're going to look at the weather features and how the weather changed. You're going to figure out what the weather condition is, and then you're going to look and see what the pollution did in response. Okay, so what we're going to do is we have 2 time frames, and the first one says time 1, and what you will do is do the full analysis of this and then fill out the sheets. And then after you kind of figure out what's really controlled, then you'll do an unknown and make a prediction. Okay, so first thing is you can take a look at one of the top of these sheets, and the top ones all the way down are going to be the weather features. So on top you have temperature, humidity, barometer, wind speed, and precipitation. Those are what you are looking at. And what we'll look at then is starting off and seeing what is changing with time. These are 36-hour periods. So what you look at is to see what changes. So do you see the changes in temperature and corresponding humidity and things like that? And with that, what we're going to do is we're going to decide what kind of condition came in. And I will tell you now, they're fronts. So you're going to look and see what happened in terms of the front and all the different features that went along with it. So once we go through here, we can then determine what kind of front came through by what air is replacing what with time. So you start here at one time, you move across to your right and see what is replacing what. Is it cold air replacing warm air, cold dry air replacing warm moist air, or the other way around? And that will be what will tell you what happens. And you can look where the precipitation occurs, whether it's a long drawn out precipitation or a very short. All the stuff we went over, that's how you can describe what the weather pattern is. The next thing you do is go down to the lower portion of the curve. And the lower portion then includes some of the basic pollutants that we see in the atmosphere. Ozone, carbon monoxide, sulfur gases, and smoke, particulates. And so you look at these then and see what occurred with this weather change. And so what you look at then is try to correspond the changes in weather with the changes in your pollutant patterns. And sometimes there may be a time lapse. So for example, if you have rain, then that comes in precipitation, does it take a while before the pollutant picks back up again? Because after all, rain should wash stuff out of the atmosphere. Does it pick up slowly? And that's a time lag. So you look down here and you have the time on the bottom, so you can pick out the time lag from going from one to the next. How far past the front does the pollutants pick up? Are the pollutants higher with this air mass, lower with that air mass? You choose and look at the things and do a kind of an analysis, a multi-factor analysis, to figure out what factors cause air pollutants to pick up. Now that's the first page. The second page will do the same thing. It's just a different situation. Once you fill that out, there will be a chart. And the chart in here asks you, if these certain things changes, what happens to the pollutants? And you can say, is it increasing? Is it decreasing? What happens with changes in these things? And that's what you're going to fill in here. And also, if you have a time lag, then you want to put that in as well. And how many hours, if you can estimate it. Do you lag things? Like, does the ozone pick up after precipitation? How many hours? And that's what you look for. The last question, on question 3, is where you take an unknown. So here's kind of a given situation with barometric pressure and a bunch of things changing. This is more current conditions. You tell me what you think the situation is as far as air pollution goes. Is this going to indicate an area of high, low, what? Okay, and so therefore we start out with things where you know, and then you make a prediction to see if you understood the process.